Let's wait for a few minutes.
Sir,
Let's wait for a few minutes. Uh, four people are joined. So, any questions?
Maybe have a painting.
Speak a bit louder. Or if you type in chat. Voice is not clear. The 6 students are there.
sir,
Yeah.
sir, for RMS value of sign variation, we should write the whole derivation or just IRMS equal to IM by root 2, which is
No,
equal to
derivation-
0.702.
Uh,
Whole derivation, sir.
no, derivation is not required. Just you have to know that.
One value.
Yeah. RMS value is 0.707.
IM.
Yeah, peak value.
Okay, sir.
Isn't the
And
peak
then on Maxwell equation, how will be the question, sir? We should write the 4 equation or we should
Yeah, you
solve
should write the 4 equations.
Okay.
Because first equation you studied in first chapter.
Okay.
Second equation in the 5th chapter, and so third equation in the EMI chapter,
Okay.
and the last equation in the 4th chapter.
Okay. Okay.
So those things you should know.
Sir, can you explain, sir?
Ah,
Can you explain how to find the wavelength, the frequency, speed, wave number
yeah.
when on that question? Sir?
Okay. See, one way is to just use that standard representation. This chapter number waves, right? See, if you have this standard waveform, see, this is a standard waveform, okay? V equal
Okay, sir.
so this is a wave traveling in the which direction? Here I put X, no. So this wave is traveling in which direction? Anyone?
X. X direction.
No, improve it. Not X. It's positive X or negative X?
Negative, sir.
Yeah.
Negative, sir.
Yeah, negative X. So just a minute, someone. Okay, so in this form, whatever is given that waveform, you can compare this thing, right? So from this, I'll get what is lambda and what is capital T, and frequency is 1 by capital T. Okay, for example, this one. Let me take this one itself. Okay, so if you compare this with this standard format, so 2 pi is missing, right? So that means whatever is there in this 0.5 into 10 raised to 3, that is 2 pi by lambda. Is that clear? You have to compare this one with this standard form.
Okay, sir.
Okay, so that means that 0.5 10 raised to 3 is 2 pi by lambda. Okay, so
Okay, sir.
that lambda is 0.5 into 10 raised to 3 divided by 2 pi. That's what our lambda is 2 pi by 0.5 10 raised to 3. That's what they have done here. Is it clear?
Okay, sir. Clear, sir.
Yeah, and time period T. So 2 pi by T, capital T should be 1.5 into 10 raised to 11. Because what is the coefficient of T, which is 1.5 into 10 raised to 11, it is 2 pi by T. So from this, I'll get 1 by T as this thing divided by 2 pi.
Okay.
Okay, frequency is 1 by T. That is basic, you should know. What I will do is do the form, right? Just a minute. So what I will do is, see, the lambda is basically space periodicity. Okay, so if we change x by x plus lambda, this argument, because other things are not going to change. So this argument should change by a amount by 2 pi, because sine of an angle is same as sine of theta plus 2 pi. Okay, so when I
Okay,
change x by x plus lambda, the extra thing I'll get is 0.5 into 10 raised to 3 times lambda. That should be equal to 2 pi. So from this we get lambda is
understood.
2 pi by
Okay, understood.
0.5 into 10 raised to 3.
0.5 to 10 to the power 3.
That's what that's what done here. Okay, so the time period is capital T. Just a minute. So time period is capital T. So if I choose, if we change T by T plus capital T, we change T to T plus capital T. So in this one, the extra thing I'll get from here is 1.5 into 10 raised to 11 into capital T, right? That should be equal to 2 pi. Because periodicity will not change. That means this argument should not change when I change T to T plus capital T. So when I put T plus capital T, the extra thing I'll get is 1.5 10 raised to 11 into T. That should be same as 2 pi. So from this I'll get 1 by T. I'll take this side. It will be 1.5 into 10 raised to 11 divided by 2 pi. That is the frequency. So they are done. Here 1.5 10 raised to 11 by 2 pi. So either you can mug up this standard form, which I don't like. I mean, I don't like to remember unnecessarily, or whatever logic I say, you can use that.
Okay, sir.
Okay, so right, you had some other doubt, no? RMS value. Yeah, for a sine wave, this is say time. So sine variation will have something like this. Then if it is voltage, means say Vm. So this V as a function of time is Vm sine omega t. So RMS means first we have to square it. So Vm square, first we have to square it. You have to go in the reverse direction. You go in this direction. So first we have to square, so we get sine square omega t. Then we have to take the mean. Mean is same as the time average. Okay, so time average of a function is integral f of t over the period 0 to t dt by the time period. Okay, and average of sine square and cos square are same, because in this same thing, if I plot cos square, it will look like this. I mean, for I put cos omega t, it will look like this. Okay, so square of sine and cos, the average will be same. Average of sine square omega t is same as average of cos square omega t. And I know sine square plus cos square is 1. So average of sine square is Vm square is not a varying, so it will come out. So average of sine square is half of average of sine square plus cos square, which is 1. So average of sine square is half. So this is, and then I have to take the root, right? Finally. So I have to take the root. This will give me RMS. Okay, so take the root of this one. So it will be Vm by root. That's will get the relation that VRMS is Vm by root. So if this is Vm, means RMS will be somewhere here. This is VRMS, which is 0.7 times the peak value. Okay. So any other question? Anyone else?
The transformer.
Who is that? Akshay.
Sir,
The transformer, the thing is, that's why we basically have a core, iron core, soft iron core. Like we have copper is a good conductor of electricity, right? So similarly, the soft iron core, soft iron is good conductor of magnetic field. or B. So if you have two coils, one is say primary, this is the primary coil, okay, and this is a secondary coil. This is primary, and this is secondary. Suppose this core was not there, so it will produce flux in all directions, right? So the field lines will go something like this. It will leave the north pole and enter the south pole, right? So everywhere in here there will be magnetic field lines. Okay, and here will so some of these field lines will link this secondary coil. Okay, but once I put this core, all these field lines will come inside this core, and all the flux will link this secondary coil. So this job, the core is like a good conductor of a magnetic field.
Yeah.
So without this soft iron core, with the number of flux linking the secondary coil, which is originating from primary, if it is say 5%. Okay, with this core, the number of field lines that are linked to the secondary coil will be 95%. So and this core is of particular material, which is soft iron. Okay, so now if I put a voltage of say VP here and say it's generating, there is some current IP. Okay, because there will be a magnetic field here, and this is a let this magnetic field have a flux phi, which is same flux which is linking both primary and secondary. Okay, so the EMF induced in one turn of this primary will be d phi by dt, and the same phi which is linking the secondary also. So the flux, the voltage per turn on both primary and secondary are same, but the voltage in the primary is number of turns is NP, and number of turns on the secondary side is NS. So this into NS. So if NS is greater than NP, then it's a step-up transformer. Okay, for example, if VP is say 10 volts and number of turns on this one NP is say 5, and if NS is say 10, then what is VS? Will be twice of this one because number of turns has doubled. So this VS will be 20 volts. Because volt per turn is same on both primary and secondary because it's the same flux which is leaking both primary and secondary. So we just take one coil of this primary and one coil of this secondary. D phi by dt is same for both. So volt per turn is same for both primary and secondary. So if primary has got less turns, say 5 turns, then the voltage will be less, and the secondary has got 10 turns, then the voltage will be twice of this primary. Okay, so VS is voltage on the secondary side, or I can write this result as VS by NS is VP by NP. The meaning of this is voltage per turn on the secondary side and on the primary side are same. That's equal to d phi by dt, which is same for both primary and secondary. So from this I get VS equal to NS by NP into VP. So if NS is more than NP, then it's a step-up transformer. If NS is less, means it's a step-down transformer. And power on the input side is voltage into current, that is VP into IP, and power on the output side is secondary voltage into the secondary current. And if you assume this transformer is an ideal transformer, then the power should be same on the input side and output side. This here neglecting the losses, so the ideal transformer. Okay, so from this I'll get just a moment. Okay, so from this I'll get IS equal to I is equal to EP by Vs, that is NP by Ns into IP. So we can see if the voltage is getting stepped up, if Ns is greater than NP, the current will get stepped down. So that the product of voltage and current is same on both the sides. Okay, so in a step-up transformer, the voltage on the secondary side is more by some factor, that factor is Ns by NP, but the current will go down by the same factor, such that the product is same as that of primary. So power on the input side is same as power on the output side. So power is conserved. Okay, because conserving does not change. So power on the input side is same as the power on the output side, and energy is also same because energy is power into time. So energy is conserved. So what I want to say is in step-up transform, just because the voltage is going up does not mean that we are creating energy. We are not creating energy, we're just stepping up the voltage. But when voltage is getting stepped up, the current will get stepped down, so that the product of voltage and current is, which is power, is same on both the sides, input and output. So we are not creating any energy by stepping up the voltage. Is this clear?
Sir,
Any other question?
Sir, the derivation of the average power of the capacitor and inductor are same, sir.
Yeah, because
Okay, sir.
it will be sine cos, no?
Power, yes, sir. Power equal to 0, no, sir, for both
Yeah.
capacitor and inductor.
Yeah,
Okay, sir. Only for resistor, it will be 1.
yeah, but resistance will be both sine and sine. So it will be sine square. Okay,
Sine
so
square.
sine square average is half.
Okay, sir.
Okay, if it is sine and cos means it is half of sine 2 theta, right?
Yes, sir.
Just a minute, I'll show it. Uh, in a resistor, if voltage is say Vm sine omega t, current will also be Im sine omega t. Okay, then the power is Vm Im, okay, sine square omega t. So this is the power is function of time. So to get the average power, how to take the time average on both the sides? So that will be Vm Im, and then time average of sine square. Time average sine square is half. So this is Vm Im by 2, which is Vrms into IRMS. Okay. So another way of understanding this thing is if this is voltage curve, then the current curve will be like this. Both are signed, right? So the power, which is product of these two, will be positive from here to here. And the second half also it will be positive because negativity is positive. So this is power as a function of time. So which is positive, right? Over this full time period. So average power is non-zero. Okay. But for inductor and resistor, if voltage is like this, the current will be cos. Sorry, this is sine, right? Voltage is sine. So current will be cos. So it will be like this. The current will be like this. Okay. So if we draw it properly, I don't think I have drawn it properly. What will happen is this part, the power will be positive. This part, one voltage is positive, current is negative, so it will be negative. So the third part, the current power will be positive, and the fourth part, the power will be negative. So average power will be 0. Here the power is always positive, right? So similarly for, I'm just showing the book. That'll be more clear. If this is for a resistor, voltage and current are in phase. So where have we done the power? Okay, okay, for capacitor and inductor, they have done it. So this is voltage for a resistor. For inductor, so when voltage is sine omega t, the current will be sine omega t minus pi by 2. Okay, so the plot of this variation will, so V is sine, I is cos. Okay, so if you multiply these two, which gives the power, it will look like this. This is V. Here you change it. V is like a cos here, and I is sine here. Okay, it can be basically there should be a phase difference of 90 degrees between voltage and current. So if voltage is cos means current will be sine. If voltage is sine means current will be cos. So here they're taking the voltage as cos, so current is sine. So if you look properly, with the voltage is positive from here to here, this 1/4 of the period. Okay, so and the current is positive. So both are positive, so the power is positive. But in second quarter, okay, the voltage is negative, but the current is still positive. So the product is negative because positive into negative is negative. In the third quarter, both are negative. Voltage is negative, the blue one, and the current is in the solid line. It's also negative. So product is positive. In the fourth quarter, both are opposite. Voltage is positive, but the current is the solid line, which is negative. So power is negative. So average power is there because plus and minus will cancel. Okay, this is for, I think they're done for inductor. Similarly, the same thing will come for capacitor. So here voltage is like this, sine, and current is cos. And here the current is leading because current has reached the maximum before the voltage has reached a maximum. So in the phasor diagram also you can see current is leading. So this is a capacitor thing. So you're multiplying the first quarter, this is the full period, this is half, so this is the quarter. So you have to divide in quarters. This is the first quarter. In the first quarter, voltage is positive, current is positive, so power is positive. In the second quarter, from here to here, voltage is positive, but current has become negative, so power is negative here. In the third quarter, from here to here, both are negative, so power is positive. In the fourth quarter, voltage is negative, current is positive, so it's negative. So power is equally positive and negative, so average power is 0 here. Okay, so voltage here they're taken as sine, and the current is cos. Okay, so the power is you have to divide in 4 quarters. This is first quarter, second quarter, third quarter, fourth quarter. So this you have to you can prove it. You should prove it because you once I have this. If you take voltage as Vm sine omega t for a capacitor, using this relation, I can get the current by differentiating this one as this one. So voltage is Vm sine omega t, current is this whole thing I can call as Im, it's cos omega t. Okay, and cos omega t we can write as sine omega t plus pi by 2, or we can just leave it like that. So basically get the power as a function of time, this one power. Okay, it's I into V. So Im cos omega t Vm sine omega t. So you have sine and cos. So sine 2 theta is 2 sine theta cos theta. Okay, so this thing can be written as sine 2 theta or 2 omega t. An average of sine to omega t is 0 because equally positive and negative. Average of sine theta is 0 and average of sine 2 theta is also 0. Okay, is this clear? This average of sine to omega t is 0.
Yes, sir.
Because if sine omega t is like this, they call this as sine omega t. This x-axis is time and y-axis is the value. Sine 2 omega t will look the frequency will be twice. So within this half period itself, the full period will happen. So it will be like this. So within one period of this sine omega t, sine 2 omega t has made 2 periods. So average of sine omega t over a period is 0 because positive here and negative here. And average sine 2 omega t is also 0 because positive, negative, positive, negative. Okay, so average of sine to omega t is also 0. So that's why the power is, average power is 0. This is true for inductor and capacitor. Because both inductor and capacitor, one is sine, other is cos. Any other
Sir,
question? Yeah.
எந்த சாப்டர் சார் வெயிட்டேஜ் அதிகம்?
I think waves is a little bit less, but questions are easy, no? I think equal weightage.
Okay, sir.
Equal weightage you should give. I've given all the concepts. Okay, you just have to apply them. And I have not given any
Okay, sir.
extra concepts also. So just what you require I've given.
Sir, any derivative?
Okay, sir. Okay, sir.
Okay.
Sir,
Yeah. See, one more thing which I didn't so far is the inductance, self-inductance and mutual inductance. So how it is defined, you should know. Chapter 6.
Sir, okay, sir.
Uh,
Sir, and any problems based on mutual inductance or
Yeah, yeah.
self-inductance, sir? Sir, can you show us how to do, sir? For example.
yeah. So also we should first easy.
Sir, and Maxwell equations. So
Yeah, just
one
write.
last time, can you explain, sir?
Yeah.
Okay, sir.
Just mutual inductance is wrong there. Spelling is wrong. See, in mutual inductance, we have two coils. Mutual inductance, we have two coils. Okay, here they have put S1 and S2. So you pass current in one of them. There is, say, you can say as input, the output, the induced voltage or the EMF in the second coil. But before that thing, we can use one more step, which is the flux linking the second coil. So the flux linking the second coil is proportional to the input, which is the current in the first coil, and the constant of proportional is the mutual inductance same to 1. Got it? The input is the current in the first coil. Okay, output is flux in the second coil. You can call it, the total flux is N2 phi 2, and the constant of proportion is the mutual inductance. Okay, so inductance, you think like this: input is current, output is the flux linking the other coil. Input is the current in one coil, output is the flux linking the second coil. Okay, and there is a constant, proportionality constant, because if the current is more, means the flux linking the second coil will be more, and the constant of proportionality is the mutual inductance. Okay, so once this thing is given, I know, so once I know phi 2, I can find the EMF of the EMF induced in the second coil just by d by dt of this phi 2. Okay, so just we check what you have to know.
Sir, that coefficient of mutual inductance,
Coefficient of
M,
there's nothing like that. What is coefficient of mutual inductance? Mutual inductance is,
M21.
is it called
Yes,
coefficient?
sir. It will. Okay, sir.
Okay, it's basically mutual inductance, which is a proportionality constant. So if this its value is
What
high,
is the value of that, sir?
that depends on, see, if they place the coil properly, all the flux which is produced by this, see, when you pass the current in the first one, I1, which is the inside one, right, it will produce magnetic field. Okay, if this coil S2 is placed properly, then all the field lengths which is coming out of this S1 will link this S2. Okay, then in that case, the mutual inductance will be high. But suppose I take this coil and keep it somewhere here on the right side. Okay, then the only a part of this flux coming out of S1 will link this S2, right? Yes or no?
Yes, sir.
Okay, in that case, mutual inductance will be less.
So they will give the value, sir.
Yes. Oh, hold on, let me
Okay, sir.
check. Yeah, the question is not difficult. See, mutual inductance will be given. Okay, and they are saying this current I1 is a function of time. See, EMF is d phi by dt, right? Where flux is
Yes, sir.
okay, phi is flux. So if the flux is not changing, then induced EMF is 0. Okay, so if this I is a constant current, then this phi 2 will be constant, but EMF won't be there. All right, because EMF is d phi by dt, d phi 2 by dt. Okay, so this current has to be a function of time. So once this current is a function of time, phi 2 is also function of time. So with that function of time, phi 2, I can get the EMF as d phi by dt. Faraday's law of electromagnetic induction, EMF is d phi by dt, right? So how I is changing with time will be given. From that, I have to find the EMF. Okay. So first thing is you have to remember this one. Okay. So once I is given as function of time, I1 is given as function of time, you know phi 2 is a function of time. After that, you can find the voltage induced in the second coil as d phi 2 by dt. And if the total voltage means it will be N2 times d phi 2 by dt. Because d phi 2 by dt is the voltage induced in one turn. They are asking the voltage of the full coil, it should be N2 times that. Okay, so this is mutual inductance. In self-inductance, there is only one coil. So the current passed through the first coil will produce a flux, which will link itself. So that is called self-inductance. Self-inductance. So here the input is, there is only one coil, so they are not put 1 and 2. So the input is the current. Okay, because it's current only a flux, which will link itself. Okay, so the output is the flux linkage, which is N times phi b, which is proportional to the input, which is I. And that constant of proportionality is self-inductance. Understood, no? In mutual inductance, there are two coils. So I'm passing current in the one coil, which is producing flux, which is linked in the second coil. The current in the first coil is producing flux linked in the second coil. But that flux itself will link the first coil itself. Okay, so current in one coil, okay, will produce flux which is linked in the same coil. So that will induce the EMF in that. That will be d phi by dt. This one. Okay. So and the direction of this induced EMF will be to oppose the change. Right. This consists with Lenz's law because there is only one coil and the current is induced in such a direction that it will oppose the change which is happening to it. See, suppose there is a coil like this, and this is the current, right? And because of this current, there will be a flux produced in this one, which is linking the same coil. Let the flux be in this direction, the magnetic field lines. Okay, so there will be a flux. Just a minute. Okay, so what I was saying. So this is flux phi, which is produced by this current, which will link the same coil. So now the EMF induced in this coil due to this flux is d phi. By dt. Okay, so this induced EMF direction will oppose this. Okay, suppose this I is increasing with time, then phi is also increasing. And suppose the direction of this here, the direction of B, because of this phi, it's upwards, right? Okay, so the induced EMF because of this one will be downwards. This is according to Lenz's law.
Sir, can you say it again, sir?
Yeah, just a minute. Suddenly I got muscle cramps. Okay. So it's not a big important thing. Okay. See, there is current flowing this coil. Okay. Because of that, magnetic field is there. That means flux is also there. And this flux is linking this coil, right? This produces an EMF. So this EMF will also drive a current. See, this I is external current. This I is external current. Okay, because of this current, the flux phi is produced. And this flux is linking this coil. So that will produce a EMF according to Faraday's law of electromagnetic induction. So that will also drive a current. It will drive a current which will oppose this effect. So suppose this I is increasing with time, then B is increasing with time. So B induced direction will be downwards. Because here B is upwards, right? Okay, so B direction will be downwards. So B induced will oppose this external B or this B to this I, the source. This is same as considered with the Lenz's law. Lenz's law, we have one external field, magnetic field, and the induced field, right? So if the external field is growing, then the induced field will be in such a direction to opposite. But say the external force is decaying, dying down, then the induced magnetic field will be in direction to support it. Right? It is the same thing here. Understood?
Yes, sir. Sir, what happened to you, sir?
I got muscle cramp.
How, sir?
I don't know. Okay, now I'm okay, a little bit okay, manageable.
You're okay, sir?
Yeah.
Okay, sir. Take care, sir.
Yeah. So just a minute. Yeah, now I'm fine. So I think the link will get cut now. So less than 1 minute. So should we continue? Just for 10 minutes or 15 minutes?
Sir, we will continue, sir.
Okay. Okay, fine. Once it gets done, we'll rejoin. Right. So any other question?